going to assume that this is the true mean and this is the true standard deviation for calcium intake for adults 60 years and older. Compute the probability that a single randomly chosen adult over 60 will have a daily calcium intake of under 400 milligrams. Okay, let's take a look at this. So I've already written down here that the mean, actually, what have I done here? It's really the population mean. This really should be mu, right? And this is already sigma. The population mean is 721, and the population standard deviation is 455. So if we look at this as a normal distribution, it's actually a little skewed, right? But we're going to ignore that for our purposes. 721 is the mean, is mu, right? And we're looking for the what percentage of the population is below 400. Okay, well, how are we going to figure that out? Well, the z-score, right? Z, because we know the population parameters, is equal to 400 minus 721 over the standard deviation, which is 454. Okay, so that's going to be equal to minus 321 over 454. So Z is going to be equal to clear 321 divided by 454 is equal to 0.707. Okay, that's our z-score, negative 0.707. So to find this area, we would go to our z-table, or we could use our Excel spreadsheet. I think I uploaded a chart with the Excel formulas embedded for you guys, I think, right? Tell me if that doesn't ring a bell with you. Let me know, and I'll go back and make sure that it's on Blackboard somewhere, or at least maybe give you guys a link to where on Blackboard where it is. Okay, so we got to look up our z-score. Okay, let's see where, if my z-table is still here somewhere. That's my t-table. Is this my z-table? I think it is. Yes, it is. So negative 7.07. Negative 0.7. Okay, so now negative 0.707. Well, actually, the closest I'm going to get is 0.71. 0.70 is 0.707 is going to be 0.70, 0.71, 0.70, 0.71. So it's going to be the closest I can get from this table is 23.89%, 0.2389. Okay, good. Okay, so let's take a look at what the next part of this question is going to be. The question has a lot of different parts. Probability of single randomly chosen adult over 60 years will have cancer over 1,000. Okay, well, in this case, we're looking at 1,000, right? So our z-score is going to be equal to 1,000 minus 721 over 454, which is going to be equal to, well, what is that? That's going to be 289 divided by 454. 289 divided by 454. Stick that into whoops. Equals. Let me clear out memory and put that into memory. Okay, so that's going to be my z-score. It's a plus 0.636. I'm going to call it plus 0.64 because I know I'm only going to get those two decimal places out of my table. Might actually be more precise to use Excel. Okay, 0.64. Where'd it go? Okay. Let me go this way, z-table. Here we go. Positive 0.64, 0.060, 1, 2, 3, 4. Looks like 73.89. Okay, if we go back to our 73, so from here down, 0.7389. So the area, the percentage of the population that would have an intake above 1,000 milligrams, excuse me, hiccup, 1.000 minus 0.7389. So that's going to be 1, carry the 1. That's going to be 9, 1. That's going to be 8, 9. It's going to be 9, carry 1, 7. It's going to be 0.27, 27.11. That area is going to be 0.2711, if assuming I'm correct. Okay, that's the probability of picking a random individual from that age group that has an intake above 1,000 a day. Okay, so for a random sample of size 50, compute the standard error and find the probability that the sample mean will be greater than 800 milligrams. Well, now we're going to take a sample of size 50, right? So we're going to have to take a look at what does that mean if we take samples of size 50, right? Sample of size 50. The distribution of samples now would have the same mean, be expected to have the same mean, 721, but now it's going to be narrower. Instead of a standard deviation for the population of 454, now it's going to have a standard error equal to 454 divided by the square root of the sample size, which is 50, right? That's going to be our standard error. So our standard error is going to be equal to, let's get our calculator back up. Okay, so I'm going to clear this, clear that. So it's going to be 454. Let's get the square root of 50 first. 50. So square root of 50 is 7.07, right? So I'm going to put that into memory. Let's clear memory. Oops, clear memory. Plus. Okay, so it's going to be 454 divided by the square root of 50. And that's equal to 64.2. I'm going to clear that now and put that into memory. Okay, so that's my standard error now. 64.2. Okay, so now I go back and I answer my question, which is for random sample size 50, compute the standard error and find the probability a sample mean will be greater than 800. Well, now 800 is here. So what's the probability that I would get a sample mean in that area? Well, what's the z-score for 800? The z-score for 800 is going to be 800 minus 721 over, instead of standard deviation, over the standard error, which is 64.2. So let's see what that's going to be. That's going to be 79 over 64.2. Okay, so it's clear. 79 divided by 64.2. Okay, that's a z-score of 1.23, right? A z-score of 1.23. So now if I go to my z-table and look for the area that's represented by a z-score of 1.23, 1.20, 1, 2, 3, it's about 89%, right? So this area to the left of this is going to be 89%, right? So that's going to leave about 11%, 0.11, about 11% of the sample means of size 50 will be above a value of 800 milligrams. Okay, not the individuals, but the sample means. Now, if I did the same thing for a sample size of 100, I would do the same calculation. The only thing that would change is my standard error. And my standard error in that case would be 454 over the square root of 100, which is going to be 45.4, right? 10 divided by 10. And we would use that to calculate my z-score. In other words, that would be 79 over 45, and that would be a t-score around 1.8 or something like that. So this is going to be moved over. So the probability for a larger sample size of getting over 800 is going to be a smaller area. Okay, so I'll leave that second part, that part of it, for you guys to calculate. Okay, but this is the standard error. I would go through the same exercise, except use this standard error. Okay, let's see if they got some more stuff, that oddball stuff that they might ask us here. Okay, and they just repeat the same. Basically, Now it's going to, it asked about that the 100 was down here. But in the interim, it asked for a couple of other values. Sample size, what probability sample mean will be less than 700. You would use the first standard error we calculated to figure out what the Z-score is there. And for sample size, probability sample mean will be between 700 and 750. And again, you would work out those two errors. I think based on what we did so far, you probably would be able to get through that. Okay, so let's take a look at number 6. A survey of 100 randomly selected workers in the food service industry that found that 60% had employer-provided health care. Calculate 95% confidence interval, the population proportion of the food service workers within employer-provided health insurance. Okay, so what do we know about this population? Well, we took a sample, and in that sample, we found that out of the 100 workers that we sampled, 60 of them had health insurance. Hence, the proportion in that industry for our sample was 0.60. Okay, so now notice I put a cap on there. That's almost like saying X bar, right? That's our sample proportion. We don't know what P is. We'll never know what P is unless we asked every employee in the healthcare industry. We'll probably never know that. Okay, so I want to find a confidence interval. Even though my 100 workers, it was 60%, what's my confidence interval for the true mean, what P really is? Okay, and I'm going to do this the same way I would normally do it with means. It's just another kind of point estimate. P cap plus or minus, right, the 1.96, I'm going to get to why I'm using that in a second, times the standard error. Okay, now standard error is calculated a special way. First, let's talk about the 1.96. When we work with a proportion, we're working with a binomial value, working with something that can have two values, insured or not insured, right? So in that case, we're going to have basically a rule that says both sides of this, in other words, you have to have at least 15 people that are insured and 15 people that are not insured to make this a valid estimate of the standard error or standard deviation or the proportion. So in this case, 0.60 out of 100, we got 60 people that are insured, and we have 40, the remaining 40 are not insured, so it's 15 in each group. So since the sample size is always going to be over 30, we're just going to use the Z-score for proportions that meet this rule. So we're going to use 1.96 for 95% confidence interval for the true proportion, or 1.64 for 90% confidence, or 2.58 for 99% confidence. So for in our case, it's going to be 0.60 plus or minus 1.96 times the standard error. Well, now how do I calculate standard error for proportion? Well, we have a formula that we learned before, that the standard error is equal to the square root of P times 1 minus P, in this case P cap, because that's what we know, over the sample size. All of this is underneath the square root. Okay, so that's going to be equal to 0.6 times 0.4 over 100, and we take the square root of the whole thing. Okay, so let's figure that out right now. Clear? Clear? Okay, 0.6 times 0.4, that's equal to 0.24 divided by 100 is a sample size equal to 0.0024. Okay, now I'm going to take the square root of that. That's all, everything that's underneath square root sign. I'm going to take the square root of that, and it's equal to 0.049. 0.049. Okay, rounded it a bit. Okay, so now I'm going to use that for my standard error, 0.049. Okay, and I'm going to say to myself, that was the number I had, right? There wasn't another zero in there, was there? Nope, that was the right number. Okay, good. So now I'm going to go ahead and resolve my 95% confidence interval. It's going to be equal to 0.60 plus or minus the value that is my margin of error. So I'll calculate the margin of error now. going to be equal to 0.049 times 1.96. I could have actually left that value in there without rounding it off in this case. So it's going to be plus or minus about 10%. Okay, so I'm gonna almost 10%. That almost is important, I think. Okay, so let's actually not in this case. 0.09. Okay, so I'm gonna say let me clear out memory. I'm gonna put that into memory. And I'm gonna clear that, and I'm gonna say okay. So our confidence interval is going to be 0.6 minus our margin of error, which is going to make it 0.05, 0.05, I'm sorry, 0.504. And the upper limit of our confidence interval is going to be 0.6 plus our margin of error, which is going to be 0.696.
Mike on it?
Okay, so based on our sample, which showed 60 people out of 100 that in this industry that had insurance, our random sample, right? Based on that sample, we're 95% sure the true population proportion for the entire population, percentage for the entire population is between 50.4% and 69.6%. Okay, and that's how we work with our proportions instead of our proportion being our point estimate instead of our mean. Okay, so now, of course, if we were working with a 90%, we would just, instead of using 1.96 here, we would use 1.64. And if we wanted a 99% confidence interval, we use 2.58 here, right? And 2.58 would make this a bigger number. It would be like adding and subtracting more like 12%. So it would be like 0.47 to 0.7 something or something like that. Our range be a wider range because that would give us a higher level of confidence that that we captured the true population proportion. Okay, so that's how we would deal with proportions. Okay, now I'm going to stop for a moment. I'm going to go over here to you guys, and how you guys feel about that? Are you okay so far? Okay, we're really doing the same things over and over again. We're just changing the values that we're using a little bit. Okay, so let's take a look at number 7. Good work. I'm glad to hear that. An exit poll of 1,000 randomly selected voters found 535 favored the incumbent candidate. Oh, okay. Is this race too close to call with a 95% confidence interval? Well, what does this say to us? What this says to us is that 535 out of 1,000 people, 53.5%, 53.5% of the 1,000 people that we selected are going to vote for the guy that we're talking about. Okay, that sounds like he's going to win the election. If you have more than 50% of the vote, you win the election by definition, right? You win the majority. The majority would be anything over 50%, right? So if it's above 0.50, right, you've won the election. The only problem is that this is a sample of 1,000 randomly selected voters. It's not really all of the voters. So now we want to see what's our 95% confidence interval for the real proportion. Well, the proportion that we got from our sample was, since sample size is 1,000 and 535, our p cap, our proportion based on our sample, is equal to 0.535. Pretty high, higher than 50%, but it's still, that's our estimate, our sample proportion, not our actual population, which we never know until they run the election. Let's see if we can't figure out what our confidence interval is going to be for this value. Okay, so how are we going to do that? Well, it's going to be p cap plus or minus 1.96, and this is, well, there's way more than 15 people in each group, 535, and the other one's going to be 465, right, times our standard error. Okay, let's calculate our standard error. Standard error is going to be equal to the square root of 0.535 times 0.465, right, 1 minus that, over my sample size, which is 1,000. Can't see what my standard error is. Should be interesting to calculate a standard error for this. Okay, clear and clear. So 0.535, right, times 0.465 equals this, divided by 1,000 equals this, and then I'm going to take the square root of that whole thing, and we wind up with this for our margin of error. So I'm going to store our margin of error in here. And now I'm going to subtract it and add it to our proportions. So this is going to be 0.535 plus or minus our margin of error. Margin of error. What's our margin of error? Margin of error is 0.01577. 0.01577. We're going to add and subtract that. Except I'm going to have the actual value here. So I'm not even going to bother around it. I'm going to leave it as it is. 0.535 minus our margin of error is 0.519, right? 0.519. Okay, so now, and the upper limit is going to be 0.535 plus our margin of error is going to be equal to 0.550. Okay, you guys checking my math? Does my math look right at this point? Okay, so we're 95% sure that P, not P cap, but P, is between 51.9 and 55.0. In other words, 51.9, 55.0. Let me just check this for a second. Clear. I just want 0.535 times 0.465 equals that divided by 1,000 equals that. Take the square root. Yep, I got the same thing. Okay. So that looks like our 95%. We're 95% sure the true proportion for the entire population is still above 50%. So it looks good to us. It looks like to us that our candidate is going to win this election. We're 95% sure that the true proportion of people that are going to vote for him in this population is between these two numbers, right? And so we're 95% sure that he's going to be above our 50%. Are we 99% sure? Well, in order to be 99% sure, we would have to go 0.535 plus or minus, and instead of 1.96, we would have to use 2.58 times our standard error, 0.01577. Well, now this is going to be a bigger margin of error, so we're going to subtract and add more than we did here. So this number is going to be a smaller number. This number is going to be a bigger number. Maybe this number is going to fall below 50%. If it does, we're no longer 99%. We won't be 99% certain that he's going to win the election, right? Well, let's give that a try right now. Okay, so let's see. Our new margin of error, okay, is going to be 0.258 minus, oops, let me clear that again, 2.58 times 0.01577, okay, which is equal to 0.217, okay, or I'm going to call that 0.22. Well, if I subtract 0.22 from something's wrong there. Let me go back on this. 2.58 times 0.01577 comes out to be 0.04, right? If I subtract let's see what happens now. I'm going to put this into, let me clear memory and put it in there. That's our margin of error now. 2.58 times 0.01577. Okay, assuming that that's right. Okay, so I'm going to do my confidence interval now. It's going to be 0.535 minus our margin of error. Uh-oh, now I'm under 50%. right? 0.594. Oh, I broke something here. Oh, got it upside down. What was it again? 494. And our upper range is going to be, I'm getting a little clumsy here. Okay, let's clear this out. Okay, it's going to be, 0.535 plus our margin of error is going to be 0.575. Well, now, are we still 95% certain that he's going to get more than 50% of the vote? Well, no, it doesn't look like he's that he's going to get 95% of the vote. It looks like he's going to fall. It's possible that he'll be outside of our 99% confidence interval. That 50% is inside of our 95% confidence interval. So we can't be sure that the true P is not under 50%. At least we can't be 99% certain. We can be 95% certain, but we can't be 95% certain. So, okay, let me get back to the comments here because I know this one was a little confusing. Do we need to multiply before adding and subtracting? Yes. Well, at one point, I lost track of where the 1.58 came from. Well, oh, this 1.58. Yes. No, hang on a second. No, did I just make a mistake there? Did I? I guess I did. You just caught me in an error, didn't I? Right. I took instead of taking the standard error, I took the margin of error from before and multiplied it by 2.58. Right. It should have been this number divided by 1,000 times 2.58. What is that number? Anyway, clear. Yeah, I think one. Yeah, so you can. It's the stand. You're right. 0.0158 is the standard error. Oh, so what did I do here? Did I forget to multiply this by 1.96? You know, I'm going through this so quickly, I kind of lost track of what I did there. Okay, let me do this. Let me calculate standard error again. Standard error was 0.535 times 0.465, right? Divided by 1,000. Whoops. I hate this calculator because you got to redo every point. 535 times 0.465 divided by 1,000, right? And the square root. So that's my standard error. So I would multiply that by 2.58 or 1.96, which gives me a 0.03, right? So I should really be adding and subtracting 0.03 from our 0.535. And, right, 0.03, right? And that would be 0.505 and 0.585, right? That's what we really should have gotten because you let me get away with that. Should have been 1.96 times our standard error. I forgot to multiply that out. Okay, and so in this case, as I said before, he's gonna win the election. It appears here with 95% certainty. But then when you do it over here, 0.258 times 0.03 times 2.8 times, what was it again? Okay, I'll do it again. 0.535 times 0.465 divided by 1,000 square root times 2.58. Okay, in this case, our margin of error is 0.4, and we did this one. This one we did correctly, right? So this one is going to fall below. It's going to fall too low for us to be certain he's going to win the election with 99% accuracy. But this one is still be high enough that we have 95% accurate confidence that he really does have more than 50% of the entire population. I hope I didn't confuse you too much there, right? You got what was going on there. I kind of like dropped a number there, but you can see what happened here is that in this particular problem, the fact that it was such a close call, we were able to see that that we have 95% confidence that the true population proportion, 95% confidence true population proportion is between 505 and 58. That means that we're 95% confidence that it's more than 50% and he's going to win the election. But when we tried to be 99% confident that it's above 50%, we saw that the confidence interval does not exclude the possibility that he could be under 50%. So we can't say we're 99% confident that he's going to win. Okay, so does that make sense to you guys? Are you okay with that, despite my having botched the calculation midway through? Okay, you guys still there? Are you okay with that? Make sense to you? Or are you still confused? Or did I confuse you unnecessarily? Okay, we got it? Okay, good, I'm glad. All right, let me just take a quick look at these other two problems. A study based on the National Health Survey, Health and Nutrition Examination Survey. 64% of adults, that's 0.64, in that age were overweight or obese. But users estimated the population prevalence for the U.S. adults. So we're going to say that we're going to assume that that's the proportion for the entire population. If a subject is selected at random from the population, what's the probability that the subject is overweight or obese? Yeah, that's just that simple. In other words, what's the probability that a random person will be overweight or obese? Well, the population proportion that's obese is 64%. So the answer to that is just 64%. That's like the middle of our distribution. If we select a person at random, half the time he'll be under 64%, half the time, excuse me, if we randomly select a person, 64% of the time he will be obese, right? Because that's the proportion that we know in the population that applies to. If 125 subjects are selected at random from this population, what is the probability that 70% or more were found to be overweight or obese? Well, how are we going to solve that? Well, that's a sample of size 125, and we know that the population proportion is 0.6, where was it, 0.64. So we can use 0.64, since we know that's the population proportion, to calculate a standard error, right? So we know 64% of the population is obese. So I could calculate a standard error using that number. If we had no knowledge of it, and we found that 70% of our sample of 125 people was obese, then I could only use that 0.70 because I don't know the true population proportion. True population proportion is 64%. So that's P. Now let's calculate a standard error for D for repeated samples of size 125. So our standard error is going to be equal to 0.64 times 0.36, P times 1 minus P, over 125, and we're going to find the square root of this whole thing. That's going to be our distribution. That's going to give us an idea of our distribution of samples for repeated samples of size 125. Okay, so let's see what we get there. this kind of a little bit of a curveball from the kinds of problems that you were getting before. So 0.64 times 0.36 is equal to that, divided by 125 is equal to this, and I'm going to take square root of the whole thing, which is 0.429, 0.0429. 0.0429. So if I want to plot the distribution of all the possible outcomes of sample sizes of size 125, well, the mean, or the p cap, the p, would be 0.64. Half the time, if I took a sample, I might find a lower number. Half the time above, because the average for the real population is 64%. Okay, so now my standard error for this distribution is 0.0429. So if you were to ask me, what's the probability that that I would take a sample of this size and 125, and that I would get a result for the proportion of those 125 people to be 70% or more overweight. So 70% would be over here somewhere to the right of the mean. What's the probability that I would get a value up in here? Okay, so 0.70. So I need to calculate a z-score for 0.70. Z is going to be equal to the value that I'm testing, which is x, minus the mean, which is the point estimate, which in this case is p. It's minus p over the standard error. Okay, so z is going to be equal to 0.7 minus 0.70 minus 0.64 over our standard error, which is 0.04. I'm going to call it 0.043. So that's going to be 0.7. It's going to be 0.06, right? Am I right there? 0.06 over 0.043. Okay, and that's going to come out to 0.06 divided by 0.043. Come out to a z-score of 1.39, 1.4 basically. So our z-score is 1.4. So if I go to my z-table of 1.40 going to represent 91.9% of the possible outcomes. So the area to the left of that is 90, what was it again? 91? Let me go back here, 91 point, where was I? 91.92, 91.919, I'll call it 91.9. Okay, and that would leave the proportion of the samples that would come up of size 125 that would come up with values above 70% would be 1 minus that, or 0.081, about 8% of the time. From this population has 64% of the people are obese. 8% of the time, if I took a sample of 125 people, I would get a result of 70% or higher for that particular sample. Okay, that would happen 8% of the time. Okay, so let's take a look at how they might build on that. C, random sample of 600 Canadians in the same demographic finds that 59% are overweight. What is a 95% confidence interval for the true population proportion of overweight Canadians? Well, now we have sample size n is equal to 600. Our proportion is that from that sample is 0.59. So we can calculate that p cap for Canadians 0.59. We can calculate a standard error, 0.59 times 0.41 divided by 600. Take the square root of that, that's our standard error. And if we want a 95% confidence interval, we would multiply that standard error by 1.96 and add it and subtract it from our 59% to get our 95% confidence interval for the true population proportion of obese Canadians. Okay, now once we've done that, we found a 95% confidence interval, which I'll leave that up to you to do the math. Now we can go to the next question. Can you say with 95% certainty that the population proportion of overweight Canadians is lower than that for Americans. Well, since you only know you know the true population proportion for Americans is 64. Now you know the 95% confidence interval for Canadians. And what you're looking for here is to see if the 64 is outside of that range, above the 95% confidence interval for Canadians, who you only know by a sample. So you have to work from a confidence interval, not from an absolute number like here, where you know that the population is 64% obese, right? Is that 64% inside of that confidence interval, so you can't really say that they're different, or is it outside of that confidence interval, which allows you to say with that level of confidence that they are indeed different? So that I'll leave that up for you to actually calculate, figure out. Based on this confidence, and what you can say about the probability, you'd be wrong if you said Americans were more likely to be overweight than Canadians. That, of course, is going to be based on whether or not that 64% is inside or outside of the confidence interval that you have for Canadians. Okay, so I'm going to call it a night there. We covered a lot of stuff here. There's a lot of different angles that we took on this, and we really only got kind of messed up in one part of one of these problems. I think we got that straight before we gave up on it, right?